In my today's lecture, I want to describe the wave energy resources. Content of this lecture is the introduction to wave energy, energy extraction from devices, advantages and disadvantages of this wave energy. Now come to the introduction of the wave energy. The wave energy is the transport and capture of energy by ocean surface waves. The energy capture is then used for all different kinds of useful work, including electricity generation, water desalination, and the pumping of water. The wave energy is also a type of renewable energy and is the largest estimated global resource form of the ocean energy. All the seas contain the energy in the form of surface waves, which can be exploited by the wave energy conversion devices. Not all the seas provide an economically exploitable resource. A good wave regime will normally be the first consideration of the wave energy resource. Such regimes are found principally on the western coast facing the world's great oceans. Wave energy exploitation is limited to the coastal and near shore sites, so the opportunity for the deployment is restricted. Even so, it is possible that the wave energy could supply up to the 10% of the global electricity demand. The development of the modern wave energy conversion technology started after the oil price rises of the 1970s. Much work was carried out in the UK, but national funding was withdrawn in 1989. The work continued in the other countries in Europe and in USA and Japan. The environmental concerns of the 1990s added further impetus to the wave energy industry, and the UK resumed funding in 1999. By the beginning of the 21st century, a wide variety of different wave generation devices were under development. By 2013, there were at least 20 competing commercial technologies in developmental operation and in commercial use worldwide, mostly of the significant different design. It will be at least a decade before the front runners become established. It is important to appreciate the many challenges facing the wave power developments. There are: number one, the wave patterns are irregular in amplitude, phase and direction. It is challenging to design the devices to extract the power efficiently over the wide range of variables. Water waves are analyzed by hydrodynamics, literally meaning the water movement, which is a subdiscipline of the fluid mechanics supported by specialist laboratory experiments and by the computational modeling. For the sea, the analysis is complicated by the distribution of wave frequencies in the location and time. These effects are modeled to obtain the dynamic forces on wave energy devices and structures that must survive for at least 25 years. A key part of the hydrodynamic analysis is the ability of a successful device to pull power into itself from a larger region of the sea than its own footprint. A measure of this ability is the device capture width. Third, there is always a probability of extreme gales or the hurricanes producing waves of the freak intensity. The wave power devices must be able to survive in such conditions. Commonly, the 50 years peak wave is 10 times the height of the average wave. Thus, the structures have to survive in siege with 100 times the power intensity to which they are normally matched. Allowing for this requires sophisticated design and testing and adds greatly to the initial cost of the wave power systems. Number 4. The peak power is generally available in deep water waves from the open sea wells produced from long fetches of the prevailing wind. The difficulties of constructing power devices for these types of wave regimes, of maintaining and fixing or mooring them in position, and of transmitting power to land are formidable. Therefore, more protected and accessible areas near to the shore are used for the prototype development and initial commercialization. 5. The wave periods are commonly 5 to 10 seconds. It is challenging to couple this irregular slow motion for electricity generation at 500 times greater frequency. Many types of devices have been suggested for wave power extraction, and so the task of selecting and developing a particular method has been somewhat arbitrary. The dedication and ability of the pioneer engineers and the financiers are vital to success. Number 7. The development and application of wave power have occurred with the spasmodic and changing the government interest largely without the benefit of the market incentives. Wave power needs the same learning curve of steadily enlarging application from small beginning that has occurred with the wind power. The distinctive advantages of the wave power are the large energy fluxes available and the predictability of the wave conditions over periods of days ahead. Waves are created by wind and effectively store the energy for transmission over the great distances. For instance, the large waves appearing off Europe will have been initiated in stormy weather in the mid-Atlantic or as far away as the Caribbean. Unlike virtually all other power generation technologies, wave energy conversion requires completely unique energy conversion devices. These devices have to convert the wave motion at the sea surface into the electricity. Now come to the energy extraction form devices. The classification of devices. As a wave passes a stationary position, the surface changes height. Small volumes of water rotate near the surface and the water pressure under the surface changes. A great variety of devices have been suggested for extracting the energy using one or more of these variations as input to the devices. So the classification is useful, which are as given below. First type of device is the point absorbers. The point absorbers, as shown in the figure, have both the width and length is less than lambda, the wavelength of the sea waves. Such devices have the large capture width to pull in power from the oncoming waves. This is the wave direction, this is the wave front, and this is the point absorbers. Second is the attenuators, as shown in the figure. This is also called the line absorbers, which are the several wavelengths long. Length is approximately greater than 50 meter and the width, narrow width, is less than lambda. The wave height reduces as the wave progresses and as power is absorbed along the length. For the attenuators to be successful, they must have a large capture width compared with the other actual width and the short length. Third is the terminators, as shown in the figure. This is the terminators. The terminators lie across the oncoming wave front with the width is greater than lambda and short length. The amplitude of the wave decreases rapidly at the interaction as power is absorbed. The wave passes on with greatly decreased flux of energy. The devices are further classified by their location, as onshore or the near shore is relatively shallow water, depth is approximately lambda, and the offshore where in the deep water the depth is more greater than lambda. A further classification relates to the development of the wave power devices are the first generation, second generation and the third generation devices. The first generation devices, these are oscillating water column, that is WOC, oscillating water column devices, having been the most straightforward devices to construct the onshore and the near shore cases. Air above the water column is forced through a turbine generator for the electricity. The second generation type of devices, the developmental floating devices, taking power from the waves to the pump internal fluids through a turbine generator. The third generation is very large single devices or as large array of the smaller devices operating commercially when the particular technologies are considered, proven and financed. Very few devices had reached this stage by 2013. Unlike virtually all other power generation technologies, the wave energy conversion requires completely unique energy conversion devices. These devices have to convert the wave motion at the sea surface into the electricity. These can be categorized in a number of ways, but perhaps the simplest is to divide them into groups. First comprises as the shore and bottom mounted near shore devices like taper channel devices, that is called TAPCHAN, oscillating water column OWN, pivoting flap devices which is called pendular, and the wave dragon floating overtopping terminator. And the second comprises that is called offshore devices which are called the float pumps, dark wave pumps and the other water snakes, piezoelectric devices and the Pelamis attenuator. Taper channel devices, TAPCHAN. The principle of the wave capture is simple as observed in many shoreline lagoons and the swimming pools. Waves rise up a channeled sea wall and the overspilling water is impounded in a reservoir above the mean sea level. Controlled outlet water returns to the sea through a conventional low head hydroelectric turbine generator. This is the reservoir. This is the wave capture tunnel, and this is the turbine house, and the water is again returned to the sea by this way. A schematic diagram of this type of TAPCHAN is shown in the figure. It is a 350 kilowatt TAPCHAN system demonstrated in Norway in 1985 and since replicated at a few sites worldwide. The devices like this usually employ a taper channel. This is the taper channel whose concrete walls reach 2 to 3 meters above the sea level. This is the concrete wall with its mouth open to the sea. This is the mouth. The side walls of the channel rise above the normal sea level, and beyond them is a reservoir. This is the reservoir. Waves traveling towards the coast are focused into the channel. As these waves flow along the channel, they become more and more restricted by the taper, and this forces the height of the wave to increase until the water starts to fall over the upper edge of the channel walls. The peaks of these waves increase in the height above the throat as the waves progresses along the taper channel. So the water spills over into the reservoir as the wave arrives at the wall. Larger waves may overtop the wall directly. This water is captured, creating a reservoir of water which is above the sea level. This water can then be run back into the sea through a hydro turbine, generating electricity. The site was chosen carefully to incorporate natural formations with the wall and basin. Sites for wave capture systems benefit from the following features, like the persistent waves with large average wave energy, deep water close to the shore so the power of the oncoming waves is not unduly dissipated, a small tidal range less than 1 meter, natural features benefiting the wave channel and the reservoir, the robust construction of the channel and the walls against the violent storms, since the storm waves are also channeled and enhanced in height towards the elevated basin. The capture length of the Tapchan device may be defined as the ratio of the average output turbine power to the average power per unit width of the waves entering the lower end of the channel. The original Tapchan in Norway was destroyed by an unexpectedly violent storm. The lessons from this are important, including the age-old device to shipping not to be caught at harbor in a violent storm when it is safer to be out at the sea. Thus, floating wave energy devices which allow storm waves to flow over them may be more robust than the rigid nearshore construction and devices. The second type of device is the oscillating water column, that is WOC terminator. Waves pass onto a partially submerged cavity open under the water as shown in the figure, so that a water column oscillates up and down in the cavity. This is the cavity. The water column is up and down in this cavity. This induces an oscillatory motion in the air above the column. This is the air, which may be connected to the atmosphere through an air turbine. This is the air turbine connected to the electricity generator. This is the electricity generator. This is the generator. This is the turbine. This is the generator, and this is the back wall. The turbine usually used in a Wells turbine, which once started continues to turn in the same direction whichever the direction of the airflow. Therefore, the generation continues without a break but at varying the power amplitude. A developmental device of this kind connected to the electricity grid operated on the Scottish island of the Islay in the 1990s for several years without damage, but at less than expected the power output. Based on that experience, a larger and more efficient device was designed and named the Limpet, that is Land Installed Marine Power Energy Transmitter. The Limpet means Land Installed Marine Power Energy Transmitter. After shellfish of that name renowned for their firm attachment to the rocks. The Limpet's general design allows for two walls turbine 250 kilowatt generators in parallel, but on Islay the site matched just one of these systems at 250 kilowatt capacity, which has continued to export power into the electricity distribution grid since 2000. Commercial operation benefited from increased export price for the electricity under the feed-in tariff legislation of the Scottish administration. An advantage of using an oscillating water column for power extraction is that the airspeed is increased by smooth reduction in the cross-sectional area of the channel approaching the turbine. This couples the slow motion of the waves to the fast rotation of the turbine without mechanical gearing. Another advantage is that the electrical generator is displaced significantly from the column of the saline water. The structural shape and the size determine its frequency response, with each form and the size of the cavity responding best to the waves of a particular frequency. It is essential that the characteristics of the turbine generator are matched to the wave movement. The third one is the oscillating flap. The energy content in moving the waves is sufficient to cause a pendulum or the flap to move the backwards and forwards. This is the pendulum, moves backward and forwards. And this too has been used as the basis for a shore-based wave energy converter. The best known converter of this type is a Japanese device called the pendular, which comprises a box open to the sea on one side, but with the open side closed using a flap hinged, this is the flap hinged, horizontally from the top. When the waves strike the flap, they cause it to oscillate to and fro like a pendulum, and this motion can be converted into the electricity using the hydraulic rams. Small devices of this type have been built and tested, and a plant of around 200 kilowatt has been designed for a site in Sri Lanka. Fourth one is the Wave Dragon, that is the floating overtopping terminator. This device was developed in Denmark, which has a coastline on the North Sea that has a less intensive wave regime than the Atlantic Ocean. It uses the overtopping method of the earlier Tapchan, but with the whole structure floating at sea. Overtopping waves spill over into the reservoir from which the water flows out through the turbine generators as shown in the figure. Low head Kaplan turbines have been used for the prototypes in this Wave Dragon. Waves are reflected and concentrated into the overtopping region by concave shaped wings. This is the concave shaped wings, and this is the also two concave shaped wings. Okay, so the waves are overtopping like this. That are all parts of the floating structure. These also give the structure greater stability, which is important in storms. After the successful prototype development of Denmark, a 7 megawatt capacity device is due to operate off the west coast of Wales. The aperture of the reflecting wings is 300 meter for this commercial scale. If the width of the active device is considered to be the sum of the turbine inflow diameters, we calculate the relative capture width ratio CWR to be about 2.4 in a 36 kilowatt per meter wave regime. This shows the benefit of the reflecting wings in the capturing power. The height of the top of the reservoir is designed to catch the overtopping from the average waves so as to optimize the generation through the year. The extended structure improves stability in rough seas, and the limited depth of the floating structure and limited height of the reservoir allow the energy of the large storm waves to pass the underneath and over the storm. The float pumps. The hose pump developed in Sweden is based on an elastic tube that ranges its internal volume as it is stretched. One end of the tube is sealed and attached to a float while the other end is open and is connected to a moored plate close to the bottom of the sea. As waves pass the device, the float moves up and down, alternately stretching and relaxing the tube. This pumps water in and out of the lower end of the tube. The pressurized water is used in a hydraulic energy conversion system to generate the electricity. This is the hose pump. This is the floating surface. Compressed seawater to generator station. This is the mooring. Reaction plate is here. The water is in and out from this narrow space. The wave power float pump developed in Denmark takes a slightly different approach. In this case, a float at the surface is attached to a rod which bears in turn on a shaft attached to a piston pump device. Movement of the float up and down causes the rod to rotate the chunk shaft, turning the vertical motion into the rotary motion from which the electricity can be extracted, exactly as in a piston engine. The Archimedes wave swing developed in the Netherlands adopts a similar principle, but the movement up and down of the buoyant floater is converted into the electricity by means of a linear. Now come to the advantages and disadvantages of the wave energy. First come to the advantages. It is renewable. The best thing about the wave energy is that it will never run out. There will always be waves crashing upon the shores of the nations near the populated coastal regions. The waves flow back from the shore, but they always return. Unlike the fossil fuels, which are running out in some places in the world just as quickly as people can discover them, unlike the ethanol or a corn product, waves are not limited by a season. They require no input from the man to make their power, and they can always be counted on. Second advantage, it is the environment friendly. Also, unlike the fossil fuels, the creating power from the waves creates no harmful byproducts such as gas, waste, and the pollution. The energy from the waves can be taken directly into the electricity producing machinery and used to power generators and the power plants nearby. In today's energy powered world, a source of clean energy is hard to come by. Third one is the abundant and widely available. Another benefit of using this energy is its nearness to places that can use it. Lots of big cities and harbors are next to the ocean and can harness the power of the waves for their use. The coastal cities tend to be well populated, so lots of people can get used to the wave energy plants. Variety of ways to the harness. A final benefit is that there are a variety of ways to gather it. Current gathering methods range from installed power plants with the hydro turbines to seafaring vessels equipped with the massive structures that are laid into the sea to gather the wave energy. Fifth advantage is the easily predictable. The biggest advantage of the wave power as against most of the other alternatives energy sources is that it is easily predictable and can be used to calculate the amount that it can produce. The wave energy is consistent and proves much better than the other sources that are dependent on the wind or the sun exposure only. The less dependency on the foreign oil cost. Dependence on the foreign companies for fossil fuels can be reduced if energy from the wave power can be extracted up to its maximum. Not only will it help to curb the air pollution, but it also provides the green jobs to the millions of the people. Seventh one is the no damage to the land. Unlike the fossil fuels, which cause the massive damage to the land as they can leave large holes while extracting energy from them, the wave power does not cause any damage to the earth. It is safe, clean, and one of the preferred methods to extract energy from the ocean. Eighth one is the reliable. Wave energy is very reliable source of the energy. It is because the waves are almost always in motion. Although there are ebbs and tides, the average motion always remains. Thus, energy can be harnessed continuously. It is a fact that the amount of energy that is produced and transported through the waves varies from the season to season and from the year to year. However, the energy production is continuous. Ninth one is the huge amount of energy can be produced. The amount of power that can be produced from the waves is absolutely enormous. It is so huge that just along the shore, the power density is approximately 30 kilowatt to the 40 kilowatt per meter of the wave. Now, as we go further deeper into the ocean, the power density increases to approximately 100 kilowatt. It is very much truly enormous. 10th one is the offshore harnessing of the wave power. The wave power can be harnessed offshore as well. The power plants harnessing the power could be put offshore. This could help in solving the problem of the power plants being too close to the land. When the power plants are placed offshore, the energy potential of the waves increases too. Since there is a lot of flexibility in the placement of the offshore plants, therefore the negative effects on the environment decreases too. The only possible problem with the offshore power plants is that they are very much expensive. Now there is also some disadvantages. Number one, the suitable to the certain locations. The biggest disadvantage to getting your energy from the waves is location. Only the power plants and the towns near the ocean will benefit directly from it. Because of its source, the wave energy is not a viable power source for everyone. Landlocked nations and the cities far from the sea have to find the alternate source of the power. So, the wave energy is not the clean energy solution for everyone. Second disadvantage is the effect on the marine ecosystem. As clean as wave energy is, it still creates hazards for some of the creatures near it. Large machines have to be put near and in the water to gather the energy from the waves. These machines disturb the sea floor, change the habitat of the near shore creatures like the crabs and the starfish, and creates the noise and disturbs the sea life around them. There is also a danger of the toxic chemicals that are used on wave energy platforms spilling and polluting the water near them. Third one is the source of disturbance for the private and commercial vessels. Another downside is that it disturbs the commercial and private vessels. Power plants that gather wave energy have to be placed by the coastline to do their job, and they have to be near cities and other populated areas to be of much use to the anybody. However, these are places that are major thoroughfares for the cargo ships, cruise ships, recreational vehicles, and the beachgoers. All of these people and vessels will be disrupted by the installation of a wave energy gathering resources. This means that the government officials and the private companies that want to invest in the wave energy sources have to take into the account and consider the needs of those they may be disturbing. Fourth one is the weak performance in the rough weather. The performance of the wave power drops significantly during the rough weather. They must withstand the rough weather. Fifth one is the wavelength. The wind power is highly dependent on the wavelength of the wave speed, the wavelength and the water density. They require a consistent flow of the powerful waves to generate a significant amount of wave power. Some areas experience unreliable wave behavior, and it becomes unpredictable to forecast the accurate wave power, and therefore cannot be trusted as a reliable energy sources. Noise and visual pollution. Wave energy generators may be unpleasant for some who live close to the coastal regions. They look like large machines working in the middle of the ocean and destroy the beauty of the ocean. They also generate noise pollution, but the noise is often covered by the noise of waves, which is much more than that of the wave generators. Seventh one is the cost of production. Although the wave energy is good on almost all sides, one of its crucial side effects is the enormous cost of the production. Energy production from the waves requires a huge setup. Also, the lifespan of the technology used is quite uncertain in these cases, since the waves are quite uncertain. Sometimes the waves can be so strong that they might severely and irreparably damage the equipment. The cost of the repairing as well as acquiring such machinery is immense. Not just that to set up a power mill to harness this energy would mean acquiring the immense cost. Also, just setting up a mill will not to do. There is maintenance to be taken care of. All these costs are really very high. So this is a very important disadvantage of the wave energy resources. So these are the references from which I make this lecture. You should go through these resources for gathering more knowledge.